Okay, hey, welcome everyone to today's Wednesday seminar. So today we have Paloma here. She is a first year PhD student at the laboratories of the Observatoire de Paris. I hope I'm butchering not too much with my French. And she's working mainly on wavelength variability from AGN jets and black hole magnetospheres, and with an emphasis on high energy phenomena. Before the PhD, she spent 1 year at the Korea Astronomy and Space Science Institute, or KASI as some might know it, working on orientation changes in blazar jets and supermassive black hole binary candidates. And I think the topic that we talked about today is a lot related to the work that she did there, but also in collaboration with other institutions. And I think the topic fits also kind of well to the already initiated year of gravity that we have here, as we have already heard about gravitational waves and how that relates to supermassive or the stellar mass black hole binaries. And now we will hear a little bit more about how to find them with electromagnetic waves. So, Paloma, thanks for coming, and the floor is yours.
Thank you, Felix. First of all, thank you for inviting me today to give this seminar. I'm very happy to be presenting this work that indeed I did mostly in KASI during my time in Korea. So this was done mostly in collaboration with Professor Bong Son from KASI and Professor Guangao Zhao from the Max Planck Institute from Radio Astronomy. So today I'll be talking about a very specific case of supermassive black hole binary candidate. It's 3C66A. And towards the end of the talk, I will also come back on candidates in general a bit and talk more about those. So the summary for today is going to be the following. I'll give a brief introduction on AGNs and VLBI. VLBI is a technique that we use to, for example, observe 3C66A. And I will start by presenting the observations of the source that we use for our study, and then talk about the analysis that we performed to understand why the jet of the source seems to be oscillating. So I'm going to come back on this. We'll look at different models that we consider, different possible interpretations, and then conclude for the source. And in the fourth part, we'll come back on supermassive black hole binary candidates, and as Felix mentioned, the different observational signatures that you can have throughout the electromagnetic spectrum and with gravitational waves. We'll look at a few more interesting candidates and talk about the need of a catalog to organize and find information on these candidates. So let's start with the introduction. We'll talk about active galactic nuclei today. So certain galaxies are observed with a very high luminosity that is, well, higher than the expected luminosity in general for the sources, higher than what is expected from stellar radiation in general. And these is due to the core of certain galaxies, which we call active. They host in their center a supermassive black hole that is accreting matter in an accretion disk. There also can be a dusty torus. There can be fast-moving clouds and slow-moving clouds further from the black hole that lead to what we call the broad line region, the narrow line region. And about 10% of these AGNs launch a relativistic magnetized jet that you can see represented on the right part of this plot. Throughout the history, with these objects were seen with very different characteristics. So at first people thought that they were different objects, but towards the end of the last century, it's been proposed that these are actually all AGNs with different features that are just seen with different angles between the objects and our line of sight. And this led to what we call the AGN unification model that allows to explain why we see a zoo of different characteristics for these objects. And the usual dichotomy is that AGNs can be classified following their mass accretion rate on one side, which will determine whether they're low or high luminosity. And on the other side, probably something related to the spin that will explain whether they're radio quiet or radio loud, because we expect the spin to, well, the presence and the strength of the spin to lead to the launching of a jet or not. And the jet is observed mostly in the radio. We'll see again this later. So this is why we talk about radio quiet or radio loud. The unification model now draws a large consensus from the community, and we can see that AGN jets are observed so for about 10% of these objects, and they were observed largely in the radio but also at other wavelengths. And this is mostly due to synchrotron radiation that goes from the optical to the X-rays. While we expect that inverse Compton radiation will lead to observations over, for example, the higher energies. And we don't have a clear consensus nowadays whether the jet is mostly leptonic or also hadronic. So this is a very open question in the field. But in any case, we know that leptonic synchrotron radiation is the main source of observed radiation for the jets. And you can see here an example of radio galaxy. This is MH7. It's a very famous AGN for which we can observe the jet at almost all the wavelengths. You have here the radio on the left, and then we go to optical X-rays and even the highest gamma rays on the right. And what is interesting is that you can see that different radio frequencies allow us to probe distinct regions of the jet. So we can see the larger spatial scales at 5 arc seconds here for the core, while we can go down to 50 microarc seconds, for example, with facilities like the EHD that I'm going to mention very briefly. So in the radio, if we want to observe sources that are compact and that are very small in the sky, so we need a very high resolution, we can use very long baseline interferometry. And VLBI basically allows us to observe these sources using telescopes that are separated by a baseline B, which can be extremely large. It can be thousands of kilometers. We can put the radio telescopes really across the globe. So this is how the EHD, basically the Event Horizon Telescope, allowed to resolve the first images of a black hole shadow using a telescope that effectively had an aperture the size of the Earth. And what basics of interferometry tell us is that if we increase indeed this baseline, we'll be able to resolve smaller details. And also if we increase the frequency, or we reduce the wavelength, we'll be able to see very small details in the sky. So look at very small resolution scales. The data that I'm going to present today for 3C66A mainly comes from two VLBI arrays. So I quickly wanted to mention those. The first is the CAVA, which corresponds to the predecessor of the East Asia VLBI network, KAVN, that today includes the Chinese telescopes, the Japanese and the Korean radio telescopes. So the precursor is CAVA, which was constituted just of the Korean and the Japanese ones. And the other array that we use the radio data of is the VLBA. So this is the very long baseline array in the United States, and it includes also a large number of telescopes. So let's move on to our source of interest for today, which is 3C66A. We'll start with the observations. So 3C66A is a BLAC object, and a BLAC object is an AGN for which the line of sight from the Earth directed towards this object is very close to the axis of the jet. So we're effectively seeing basically the jet coming towards us, and this leads to a lot of interesting effects, such as Doppler boosting that, for example, would lead the jet coming towards us to be very bright, while the counter jet going against us to be very weak or not observable. And so this BLAC object is found at as a redshift of about 0.34, even though it's a bit of an uncertain value. And at this distance, 1 milliarc second approximately corresponds to 5 parsecs. This object is a very famous object in the radio. It's been observed previously. It presents numerous bendings and complex kinematics. So there are components that are seen to be superluminal, so to go with speeds higher than the speed of light. Some components have been traced and show motions that are transverse across the jet or even going back towards the core. So it's a very complex source. And this Cava data that I'm presenting here is from 2014. And we have three different epochs that show us that actually, if we look at the top panel at higher frequencies of 22 gigahertz, we see that the jet seems to be twisted. So in this sense, twisted means that we see bendings that occur in different directions along the jet, and that looks like a bit of a wobble. And this twisted structure is also reported in the VLBA data that I'm going to present. And it's one of the main findings that are going to allow us to interpret what we observe. So we also considered VLBA data, and in this case, instead of just 3 epochs, we looked at 29 years of 43 gigahertz data. So we took archival data, and what we did is studied the evolution of the position angle, which basically determines the direction of the jet compared to the core. Over these 29 years. And we studied the position angle evolution for different components along the jet, mainly a component that is very close to the core that we call the inner jet, a component a bit further away from the core, and a component much further away. And these 3 components were studied with 2 different methods. One is the typical circular Gaussian fitting with diffmap, which allows us to fit the jet with different Gaussians and obtain the position angle from these Gaussians. And another method for which we give the results on the right panel here is annular bending. So in this case, we consider a certain distance from the core. We consider a bin, literally around, that correspond to the same distance as the components we obtained with Gaussian fitting. And we look at the average position angle for the data in this region. And in this case, what we find is that the 2 regions close to the core both oscillate and decay, and we obtain the same results with the 2 methods. So you can see here on the left panel, for example, in red, the J1 component that is the inner jet, and in orange, the J2 component that is slightly further away. And these 2 components look like they oscillate. We can fit them with sinusoidals and linear decay, while the furthest component from the core looks like it's decaying linearly. We can fit the data and look particularly at the inner jet data. So the inner jet position angle seems to oscillate every 11 years. And to make sure that this isn't just oscillation that looks like it's present and that we can just fit with a sinusoidal, we also looked at, we used periodicity search methods, 3 different ones, to confirm that this is a periodic signal that is detected with a 5 sigma significance level. And we accounted both for white noise and for red noise in case of stochastic noise. So this seems to be a solid result. And the amplitude of this oscillation is of about 8 degrees, while the overall reorientation of the position angle is of about 0.8 degrees per year. We can also look at the flux density for this source. So the flux density seems to be core dominated, as you can see in the bottom plot, with in blue the total flux and in black the core flux. And we see that it is highly variable with time. We also performed a periodicity search for the flux for 3C66A. And in this case, we found 3 possible periodicities of about 3, 7, or 10 years, but we only find at 2 sigma significance level. So this is not a significant detection. And we were still interested in seeing whether there is a correlation between the flux and the position angle change. And we did a discrete correlation function analysis that, again, revealed a possible 2 sigma detection correlation between the core flux density and this inner jet position angle. On top of the radio data, we wanted to have a look at other data to be able to have more confident more confident results in our interpretation. So we looked specifically at a paper by Mohana et al. In 2021, where they showed that across all wavelengths, especially in the highest energies here and in the optical, there is a sudden drop that seems to have been observed at this epoch, which corresponds approximately to 2010, when we observe a strong position angle, well, the peak of our position angle, and then a decay in the position angle for the inner jet. And the authors of this paper argued at the time that this was likely due to either a change in Doppler factor or a change in the inclination of the jet. So this seems to indicate that a geometric origin for the flux would be consistent with what we observe in the jet position angle change. And we can also look at optical data for which many papers throughout the past more than 10 years now have independently reported the presence of a periodicity in this data. And Cheng et al. 2022 looked at all these different papers, and they did their own periodicity search as well. And they claim that there is indeed a clear 2-year periodic signal observed for the light curve of 3666A. So they and previous authors also argue for a possible supermassive black hole binary that might be leading to this periodicity in the light curve. And we take all of this together and we try to understand why the jet of 3666A seems to be oscillating, and whether we can reconcile the different observations in the different bands and for the position angle and the flux. So the fact that the position angle oscillates, that we see this drop in multi-wavelength data, and that there is a 2-year optical flux periodicity that can match the periodic value of 11 years in the radio if we correct for redshift F and for Doppler boosting. We have a strong case for geometric induced scenario for these flux changes. So we interpret this as a jet that is actually precessing, and that is the cause of most of the observed periodicity signals in the optical and in the position angle for in the radio. So we see that there is a clear oscillation of the order of 10 years, and we also have a decay that seems to be occurring on a much larger timescale. So what we do is that we interpret the position angle data as a jet that precesses actually over 2 timescales. So this decadal one, for which we see almost 3 periods, and a secular timescale of about 500 to 1,000 years, of which we would only be seeing here a small fraction through the decay over these 30 years of data. We only have 30 years of data, so what we do is that we choose to fit our data with a precessing model, but only for the 11-year period. So we consider the decay to be fixed, and we just fit the decadal periodicity with this precession model. Here you have a scheme for the precessing geometry that we consider that was applied before for other sources which presented a similar position angle periodicity in their data. And we use constraints from the fact that this is a BL-like object, for which we know that the viewing angle must be small, and we obtain the following values for the jet, mainly a small half opening angle for the cone of the jet, and a precession period that is indeed of the order of 11 years. The fact that we observe 2 timescales in the position angle change for 3666A leads us to consider very quickly a supermassive black hole binary case, because what is very compelling is that you can explain using a binary model different periodic orientation changes, but also different values of the periodicity in the flux, for example. In the case of the jet, these orientation changes can be caused by the orbital motion of the primary black hole, so the black hole that is assumed to be launching the jet, It can be caused by a misalignment between the spin of this black hole and the orbital plane, but also between, for example, the accretion disk of this black hole and the orbital plane. And for the flux periodicity, well, this can also be caused by for example, precession of the jet caused in the system, but it can be related to perturbation in the primary's disk or in a circumbinary disk that includes both black holes. So you have a lot of different mechanisms that can lead to these timescales observed, which in a way is both what makes the binary model very interesting. It can explain all of the different phenomena that we observe, but it's also tricky because it becomes hard to disentangle between these phenomena to be able to say exactly within the model what is causing what. What is interesting is that there's been a lot of sources already that present similar position angle changes that have been observed for 3C66A. And in all of these cases, the binary hypothesis has often been brought forward. This includes the quasar S5-1928, for example, in a series of paper by Kuhn et al., where they also see, for example, the position angle here at the bottom in blue that both oscillates and has a linear change in time. In their case, it's a linear increase. It's also the case for OJ287, which is considered the most promising binary black hole candidate. Also, other famous sources like M81, and many more. In the case of 3C66A, we want to understand what specifically can cause the position angle change that we observe in the jet within this binary model. And what we look at is the timescales, because this is basically the only information that we have from the periodicity of our data. And what we find is that we can explain the short term, so the 11-year period with orbital motion of the primary black hole. This leads to an expected black hole mass for 3C66A that matches the mass that we have estimated for the source. And we considered for the long term, so the secular periodicity, either disk orbit or spin orbit precession. And we rule out the case of spin orbit precession, so misalignment between the spin of the black hole and the orbital plane, because it would lead to a periodic timescale that is orders of magnitudes above what we observe for our source. Well, we checked that the timescales for misalignment between the disk and the orbital plane matches very well the expected timescale of 500 to 1,000 years for the long-term periodicity of our source. From these, we can estimate some parameters for the system. And here is a table with the expected parameters for 3C66A, if this is indeed a binary, supermassive black hole binary. Mainly, the separation would be of the order of 10 to the minus 2 parsecs, and the post-Newtonian parameter is of the order of 10 to the minus 4. So we're almost at the phase where the binaries are really gravitationally bound, and they're not at all, and they're really just emitting gravitational waves and merging closer to each other. If we assume that we are reaching this stage, then the merger timescales is of the order of 900 millions of years. We can also measure it based on these values, the strain amplitude for the system. So the strain amplitude is a dimensionless parameter that gives us an idea of the amplitude of gravitational wave signals we would observe coming from such a source. And in this case, it's 10 to the minus 19. So if we place this value in this plot for the gravitational wave strain versus the frequency, we see that 3C66A falls on this yellow circle here. So it looks like it would be very difficult for current and even planned facilities for pulsar timing arrays to be able to actually say anything about our source, whether it's a binary or not, whether it can validate or invalidate the presence of a binary. So this is sad, but it's somewhat expected. So the binary possibility is very exciting. It's very compelling because there is no real candidate that has been definitely confirmed yet, but it's only one of the possible mechanisms that can explain the variability that we observe in the position angle and in the flux. Sorry, I'm just going to drink some water. But there are many more effects that don't require a binary system that could explain the different periodicities that we see. So the first one is lens staring effect. In this case, lens staring precession. So this corresponds to the precession of an accretion disk that would be misaligned with a single black hole spin. This is called Barton-Peterson. It's the generalization of the lens staring effect that would occur for just, let's say, a particle that is orbiting misaligned with respect to the spin of a Kerr black hole, and that you generalize in the case, yes, of this viscous accretion disk, where the whole accretion disk can be considered to also be precessing. And actually, several GRMHD simulations have shown that if you have such a configuration, such a misalignment, you can lead to precession of the entire disk jet system. So this could lead to the jet to also precess, and so it could explain the oscillating jet in our case, just as it has been used to explain, for example, the oscillation of the jet of 3C45 4.3 or M87. So in the left plot, for example, here, you can see data for the position angle of M87 over time. And in this paper, the authors argued that the period that is observed in this case can be explained with the lens staring effect in the source. And this doesn't require a second black hole. So it would be another viable explanation. And in our case, we checked whether the lens staring effect can explain our periodicity, mainly looking at the timescales again. So here on the left, you see plots where for a given, so we considered two different density profiles along the disk, a power law and an exponential. And the top shows, for example, the power law case where you can see the period as a function of the spin of the black hole. And what we find is you can see here in black the 11-year period and in gray the about 1,000-year period. We can explain the periodicity observed both on long and on short timescales for different parameters of the spin and for different density profiles of our disk. So the lens staring effect can indeed explain the periodicity observed on both timescales, but it would require different properties, of course, for our system. So it can explain either the long-term or the short-term periodicity observed in the position angle change. And we actually find that in the case of a power law density profile, the parameter space allowed is larger. So it's also the favored mechanism. It's the favored description for the disk. We can consider, on top of the lens staring, other disk or other jet instabilities. One of them is disk-induced precession. So in this case, what we consider is that we have a massive outer disk that is misaligned with respect to the inner disk. And if this massive outer disk has large enough angular momentum, it can also lead to precession of the inner disk and of the entire disk jet system. This, however, cannot account for any of the observed periodicity in 3C66A because it would lead basically, if we see, for example, on this plot, it would lead to our black hole having almost null spin. So we can't explain the position angle change that we observe with this. But there are other instabilities, for example, occurring in the jet itself that could explain what we observe. One of the most considered instabilities to explain strange morphologies or oscillating jets is the current-driven kink instability. So this instability develops when there is a strong toroidal magnetic field, and it leads to transverse displacement in the plasma column of the jet. So it can lead to helical jet distortion if the right conditions apply. And this has been, for example, used to interpret a quasi-periodic flux oscillation in the Biela-Carté for something, however, that was on a very short timescale of about 13 hours. And in our case, we checked that the growing timescales for the current-driven instability can fit the properties that we know for the position angle change that we observe in the case of the 11-year period. However, we should keep in mind that this instability requires a strong toroidal magnetic field, and it's not certain that such a strong magnetic field would be present at the distance where we observe our periodic pattern. Another instability of interest is the Kelvin-Helmholtz helical instability. So this arises at the interface between the jet and the external medium when there is a velocity gradient. And the helical mode of the Kelvin-Helmholtz instability has been used to explain twisted structures and jets that swing, so that oscillate, in particular for 3C449, but also to explain the quasi-periodic orientation pattern in MT7. So you can see here on the right the plot that shows the offset from the center of the jet of MT7 at different distances, and it looks like a wave propagating indeed along the jet. And this was interpreted as Kelvin-Helmholtz instability in this paper in 2018. And this is the same source for which the periodic pattern was actually interpreted as lens-staring instability. So this shows that there is still a lot of debate going on. It's very hard to disentangle between the possible mechanisms that can explain these patterns. And in our case, the Kelvin-Helmholtz instability can again explain the short-term periodic pattern of about 11 years, but we have to assume certain specific conditions for the jet. For instance, it should be in the Alvenic limit out to a quite large distance, and we have to assume that the external medium of the jet is of comparable magnetization to the jet, which could be the case if, for example, there is a cocooning medium around the jet. But all of these give extra constraints for believing that this instability is indeed responsible for the period that we observe. Another instability of interest is radiation-induced disk warping. So this is quite specific. The idea here is that if you have an accretion disk that is non-planar or that is warped, so around your central black hole, and it's optically thick, it's actually going to be unstable to this non-planaricity because you're going to re-emit radiation that has different intensity in different parts of the disk. So as you can see here, for example, in different annuli, and it will lead to further warping. So further instabilities that could lead to the precession of the disk. So again, we could assume they could lead to precession of the jet as well. This has been used as interpretation for precession inside the NGC 1275 galaxy. But in the case of 3C66A, if we look at the timescales, it seems that this would lead to a precession on orders of magnitude larger than both the 11-year and 100 or 1,000-year periods that we observe. So we can rule out radiation-induced disk warping. So if we take it all together, it looks like among the instabilities, the only two that could explain that could explain one of our position angle changes is the current-driven instability or the Kelvin-Helmholtz instability, although they require specific properties for the jet that we can't exactly verify at the stage. And these can only explain the short-term periodicity, so of 11 years. Wrapping up, if we want to put it all together, 3C66A has a twisted jet that is a morphology that is very specific, that has been observed for other sources, but it also presents a periodic position angle change on two timescales, one that is of the order of 10 years and one that is of the order of 100 to 1,000 years. And it also presents known flux periodicity and possible radio periodicity. And this can be interpreted as, if we want a parsimonious explanation, a precessing jet in a supermassive black hole binary system, or within a more complex situation, a jet that is precessing due to the lens-staring effect on the long term, and on the short term, this would be combined with, for instance, current-driven or Kelvin-Helmholtz instability propagating down the jet. So that's it for 3C66A. And now we can have a quick look at other supermassive black hole binary candidates, and this will be our the last part of this talk. So Supermassive black hole binaries are expected to form at the center of galaxies when we have the merging of two galaxies. This has been proposed now almost 40 years ago, but funnily or interestingly, since then, we have had a growing number of candidates that have been proposed, but there is no clear evidence for a hard binary yet. So a hard binary is, in this sense, a supermassive black hole binary where we consider it to be the two black holes to be gravitationally bound, and this occurs usually on scales of 1 parsec or less. While we call dual AGNs that, so black holes that are both AGNs, which can be resolved now with several techniques. And they are resolved because they have a separation that is typically of kiloparsecs, sometimes down to 100 parsecs, or even less in the smallest scales that has been resolved of about 7 parsecs. But we haven't been able to resolve anything below this range yet. And here on this plot, that comes from a very rich chapter by Durazzo and Crazy in 2023 that I highly recommend if you're interested on the topic. You can see here dual AGNs represented with the green crosses, so some of the AGNs that have been observed. The hard binary limit here in gray. And below this hard binary limit, you have a number of sources represented here with different colors and different shapes that correspond to candidate supermassive black hole binaries that have been reported in the literature. And these candidates are being reported more and more often, and they can be reported with different observational signatures, so through different mechanisms, through different methods. One of them is first particular morphologies of the jets. So jets, we said, only appear in about 10% of AGNs, so this is a small fraction of the overall population. But it's interesting because we can observe them fairly well using VLBI, for instance. And jets that present helicity, so helical jets that present, let's say, twisted structures or wiggling patterns or other complex morphologies can be associated with supermassive black hole binaries. And there's been a number of them that has been detected and that are claimed to be possible candidates. And you can see some of them here in yellow with the crosses. This is, for instance, the case of 3C66A. And another method that can be used, so one thing about the jets is that this is obviously indirect, and also, as we just saw, it's definitely not unique. So these signatures of, for instance, twisted jets could be caused by a lot of other mechanisms that don't require a binary. So they are not firm evidence for hard binaries. Another observational signature that is used to detect binaries is periodicity in especially light curves. So this can be at different wavelengths. It's most often in the opticals, sometimes in the X-rays. And the periodicity itself is hard to detect because these sources are highly variable. They present a high stochastic variability. So it's also difficult to ensure that what we are observing is a periodic signal and it's not just noise. This requires, specific methods to be applied to the data. And what is nice with this approach is that you can look at surveys that have been done, for example, with the Catalina Real Transient Survey or Zwicky or other surveys. We have a lot of data for thousands of sources, so you can go and for each source, look at the signal, look for periodicity, try to account for the noise, and check whether you find a signal that looks like is significant. And in this way, there's been hundreds of sources that have been reported as possible binary candidates, and they're given here in green or in magenta from different surveys and from different papers. These, again, the periodicity in this case can come from several mechanisms going on within the binary system. It can be from Doppler boosting, it can come from the disk, it can come from the jet. It's sometimes also hard to disentangle, but it's supposed to give different signatures in the periodicity observed. Another observational signature is in spectral shifts. Here, mostly it's expected to come from the emission line of the ionized gas close to the black holes, so the broadline region. And one can look at different, again, signatures in these spectra as well. You can have, for example, lines that are doubly peaked that could come um, from like sorry, emission line regions from both black holes, but it could also come from comparison between, for example, the broad emission lines and the narrow emission lines. So the broader would be expected to be seen as changing, for example, within a binary system moving with the primary black hole, while the furthest lines associated to the narrow line region would expect not to show this variability. So you can have several effects that are observed, and that can give you candidates to massive black hole binaries. And there has been, in this case as well, a lot of systematic searches using spectral data from surveys. And this has led to many candidates that have been reported that are not visible here in this plot. And finally, from the electromagnetic spectrum, you can use VLBI astrometry to try and detect supermassive black hole binaries. And this is one of pretty much the only clearly direct and unique way of finding hard binary using the electromagnetic data. So the idea here is that you use VLBI to really resolve two cores of the two AGNs, and you follow, for example, the cores throughout long enough time so that you can see the orbital motion that's being traced by these cores. This, of course, implies that both black holes in the system must be radio loud, which is not a given. And also, because we want to detect hard binaries, we know that these will have a very small separation, so they're going to have a very small projected separation in the sky. And using VLBI astrometry to detect supermassive black hole binaries, therefore, is really just limited by our current resolution. The the highest resolution that we can achieve is of the order of 10 microarc seconds with the HT nowadays, for instance, and this is really the limit of supermassive black hole binary that would have to be relatively close to us that we would be able to detect. And another downside in this technique is that it's very expensive. We can't do like for periodicity in light curves or spectral lines. You can't just use surveys to have systematic searches. You really need to choose a source and observe it regularly and be able to have enough data over, for example, periods that can be of the order of 10 years or more to be able to have a clear detection. So this is a very specific and time-demanding observation. Finally, we can look at gravitational waves. So if we go to multi-messengers, gravitational waves can really give us unique signatures for supermassive black hole binaries. They will be able to definitely give answers on the presence and the rates of mergers of these objects. And we can, for instance, consider LISA, which is a planned space interferometer that will allow us to observe, for instance, these sources for the smallest masses of black holes and also the smallest periods. But LISA is still relatively far away from us, and currently one of the most promising ways to detect supermassive black hole binaries is using pulsar timing arrays that effectively is a method using pulsars as clocks that would allow us to detect possible signals of gravitational wave signals from binaries that are emerging or that are in a hard binary phase. And we expect in the coming years to be able to detect, hopefully, first supermassive black hole binaries with a firm detection using either astrometry or PTAs, even though we currently don't have such a detection. But using pulsar timing arrays, actually, there has been a background detection that has been confirmed that seems to be coming from an overall population of binaries in the universe, which is already a very exciting result. I feel like I'm going maybe a bit, I'm afraid I might go out of time, so I'll try to be fast on this. I quickly wanted to talk about two candidates. One is OJ287. So this is considered to be the most promising supermassive black hole binary candidate because it has a very clearly detected periodicity in its optical light curve, and it has a double periodicity of about 60 years and of about 12 years. And the light curve, the periodicity of 12 years itself presents double peaks that you can see here in the zoom in on the left panel. And the overall understanding of this is that you have a supermassive black hole that is a secondary that is plunging onto the disk of the ultramassive primary every about 12 years in this eccentric orbit. And this leads to the plunging of the secondary onto the disk leads to hot bubbles that are released as the black hole plunges that leads to this extra emission observed as these peaks every 12 years. This is a very compelling scenario because we see these peaks coming back regularly, so this is really confirmed. And there's been a lot of studies that seem to favor this model. But if we look at, for example, the radio side with the VLBI, OJ287 also shows a jet that is oscillating actually over two timescales of about 30 years and of a few years. And in this case, for instance, Britson et al. In a series of papers have shown that this can be explained with a precessing jet, and a jet that is both precessing and has also a short-term nutation. And this can indeed be be occurring in a binary system, but this could also just be caused by lens staring, again, in a single black hole system. And they argue that the different orientations of the jets could also explain the observed variability on the optical. So it's still not certain whether the observed variability in the light curve and in the jet for OJ287 is, for instance, a binary system, although it is a candidate. But what's exciting is that OJ287 is also quite bright, and it's the expected separation from the models from these flares is of about 27 microarc seconds. So hopefully in the future we'll be able to actually look with the VLBI at the source and potentially observe two cores or not, which is not given again in case the secondary black hole is not an AGN, so is not radio loud. Another very interesting source is 0402-379. This is famous for being the closest black hole pair that has been observed. In this plot, it is this green cross here. So it's not, well, it's at the limit of possibly being a hard binary, but it's still very exciting because it's only a projected separation of 7.3 parsecs. And the authors have shown that the cores that are resolved here are compact, they have flat spectra, they have a variable flux, and especially they seem to be fixed with respect to these larger hotspots that are moving, and that seem to be the jets coming from one or other, or only from one of the black holes. So this seems to be a very clear case of two black holes that have been resolved with the largest, with the smallest separation to date. This happened in 2006, and later in 2017, it was actually found that you can correct these cores for core shift, and there seems to be a relative motion between the two cores that has been interpreted as the motion as orbital motion within a binary system by Bensarela et al. And this gives some specific values for the binary system, which are still debatable. For instance, this seems to require primary black hole mass that is very large, of the order of 10 to the 10 solar masses, which is a bit uncomfortable. But this shows the potential of VLBI for resolving and tracking possible supermassive black hole binaries. All of this to say that there are a lot of different methods that allow us to report candidates, and these can be reported through systematic searches or as individual candidates. But for now, there are no confirmed sources. And it becomes very clear throughout the literature that we have a lot of data and a lot of information that is scattered across papers and reviews. And it would be helpful to have a catalog that allows us to find easily the information for these sources and to compare what has been found in different wavelengths, for example, through different observational methods, and what values are expected from several models for example, the mass of the black holes, their mass ratios, their separation, their periodicity. And this would be especially interesting if, for example, we wanted to use PTA or VLBI astrometry to consider a specific source and point at that source and be able to say something about whether it's a binary or not. So with this in mind, I started while being in Korea working on a catalog that regroups, for now, individual candidates and regroups the different references that have led to evidence in different bands, and also references that challenge the presence of a binary system, for example, explaining alternative interpretations for the characteristics observed. Um, and this is an ongoing work that is now also being done with Felix at EF Worth and other collaborators in Korea. And the idea is to update this catalog, including all the sources that have been reported as candidate individually, and make it public, because we are currently just using it internally. But we would like to make it public, especially because we would like to make it available for people in the VLBI and PTA communities that might be interested in finding specific sources of interest for their observations. And it's hard to pinpoint sources when you have to go through so much literature. So here, for example, are some preliminary plots that show a number of candidates that have been reported, and we can measure, or we can at least estimate the strain parameter and their chirp mass, or more of interest for radio VLBI community is a list of candidates for which we plot, for instance, the period of the binary, the angular separation, and the radio flux expected, because we might have a small period and a large angular separation expected, but if the source is way too quiet, is way too faint in the radio, then we won't be able to observe it. And recently, we've actually realized that there's other people who are working on similar catalogs. That we know of, there's two that are also in preparation, so they haven't been published yet. There's the Big Mac book multi-AGN catalog that won't just include supermassive black hole binaries, but also dual AGNs and other like dual other types of multi-AGN systems that are not dual AGNs or supermassive black hole binaries. And there is Bobcat, Black Holes Orbiting Black Holes catalog, for which there's no publication yet, just an abstract. But it looks like they're also going to have a public catalog coming up at some point. We are not sure when. But if this interests you, you can keep on looking for these. So to conclude this talk, we have specifically focused on 3666A, which is a BLAC that presents morphological and periodic evidence for a binary system, where the jet oscillates on two timescales that are of about 10 years and of a few hundreds of years. And this can be associated with orbital motion of the primary and misalignment between the disk and the orbital plane. But there are also other interpretations that could explain the different characteristics observed, which don't require the presence of two black holes. And these are mainly different types of instabilities in the jet. And beyond 3666A, there is a growing number of supermassive black hole binary candidates that is being reported. And this is being done with a lot of different methods, but it's still hard to find definite evidence for binary candidates. And we expect mainly VLBI astrometry and pulsar timing arrays, and in larger future also LISA, to actually provide direct and unique evidence for these binaries. But these very numerous candidates make it clear that we are needing a catalog at this stage to allow for different communities to select potential sources, to cross-check with their own methods, and to find the relevant information for them. to actually be able to say something about these candidates. That's it for my talk. Thank you for listening, and if you have any questions, don't hesitate.
Yes, thank you very much, Paloma. It was a very interesting and extensive talk. And I think we understand now how difficult it is to confirm or reject a possible binary as such. Are there any questions? Don't be shy. Otherwise, I'll ask one. Um, you mentioned instabilities and specifically kink instabilities as a possible explanation for jet position angle changes. So, yeah, this, as you said, this requires a strong toroidal magnetic field. So, did you look at polarization data, for example, to see if this is true in this source?
No, we haven't looked at the polarization data yet. This is definitely something that we would have to do on follow-up work to be able to have better constraints on these different mechanisms.
Yes, I think probably the source would also be in the Mojave database.
Yes,
So this would also be worth checking, I guess.
yes.
I have more questions if no one else wants to ask one. Um, I know that because spin estimates are hard to come by in sources, but is there anything like from X-ray reflection data or so for spin estimates for the source?
For this source, no, we don't have a spin estimate. So what we do is that we actually consider the spin. So in this table, for instance, um, we no, we don't really have any estimates. In fact, we just it's a free parameter of our model.
It would be interesting to, since your different disk densities, density profiles, they yield more or less more freedom on the spin to vary or not. Like it would be interesting to see where where the actual value would be. But I think
Yeah,
for many sources by now we
it's
think
very
that the spin
difficult.
should be higher.
Um, Honestly, I am really not convinced by giving a range for the source at all. All that we can say is that it's most likely not 0 or of the order of, let's say, 10 to the minus 7, which is what, for example, would be required for certain of our interpretations. It's most likely not 10 to the minus 7, so something indeed between, well, 0.1 and 1. But we don't have an estimate. We would be able to give an estimate if we had, for instance, a better constraint on, I don't know, on the disk, and if we were certain that the lens tearing effect were causing, for instance, either the short or the long-term periodicity. But we really don't know for sure.
Yes, okay. I understand the uncertainty. Okay, if there are no more questions, I think we're at the hour of the talk, so it's time to wrap up. So thank you again, Paloma, for this great talk. And yeah, I think it concludes our seminar for today. So
Thank
thank you
you.
for coming.